Yes, they started in 1983. It's one of the fastest growing analog companies. 9.7 billion market cap with an annual revenue of almost 2.3 billion. And they have a headquarters in San Jose in California. The technologies that they participate in range from healthcare, wearables, data, communications, lighting, automotive, battery and industrial, smartphones, and their latest technology is the solar technology, which we'll cover today. So now let's look at these evolution. So with the normal solar panels, what happens is the cells are combined into strings. Strings are then combined into modules, and you have a bypass diode across the individual strings to help limit shading. So you can see here there's the bypass diodes for the strings. Now what happens in a shading situation, if any shade falls across the module, you lose 1/3 according to each string that's shaded. So your entire string will lose 1/3 of the power of one string shaded. The entire string loses 60% of the shaded. Your entire string loses its power. So if you look at your conventional junction box, you've got the diodes across each individual string. The next evolution was solar panel optimizers. Now, what the optimizer does is it will optimize the power across one module, but it still incorporates the junction box with the diodes. So the latest evolution is solar cell optimizers, and what this does is it's a much finer resolution. So each string has an optimizer built into that. So how would that work? Once again, if you look at your conventional solar panel, if you have any shading across your string or across a cell, your entire string loses its power. Your bypass diode goes into forward conduction, and your module will lose 30% of its power. If we look at a module with a solar panel optimizer, you actually see the same effect. So one cell gets shaded, your bypass diode will go into forward conduction, and you lose 30% of the power in your module. If we then look at a module with a solar cell optimizer, what will happen is your two strings still perform normally. Your third string with the shading on the cell, it will then reduce its power, but not entirely. So it's limited by the amount of shading per cell. And what that helps us to achieve is a much higher output when you have some kind of a shading condition. So the other advantage is if you look at a conventional panel, the power will be determined by the worst performing cell inside that module. So the panel performs according to that cell, and degradation over time will be determined by the weakest performing cell. With a module where you have string level optimization, your degradation and power is determined by the worst cell in each string. So what that does is it limits the impact of the worst performing cell, and it enables the much better performance over lifetime and gives us better energy production over the lifetime of that particular solar panel. The next benefit of the optimizers is that we eliminate hotspots. Now, how does that work? In a normal cell, if you have a shading condition, your cell effectively becomes a resistance in the module, and the only way for it to get rid of the power or the current that's passing through it is to heat up, and that is why the hotspot is created. With the solar cell optimizers, what happens is the power is reduced proportionally according to the shading on that particular cell. What this means is that your current is reduced, and in that string you will not get the hotspots developing because the entire string is performing according to that particular cell that is shaded. So you're not forcing current through the solar cells, and by not forcing the current through those solar cells, you don't get the hotspots developing. So let's look at the output power with that particular leaf obstruction. So if you look at the first example, it's this blue line here on the graph. So looking at the module current, where you have that leaf obstruction, you have this little knee in the curve, a drop in the current, and then the current is limited and drops off quite sharply. The benefit of the panel with the solar cell optimizer is that by bypassing the weaker cell, we get a much better current performance, and then the power flattens out, the current performance flattens out, and we get a much better power performance out of that module. So effectively, this entire area here is increased production and performance outside of that solar panel. Where this has a huge benefit is not only the power production, but in your operation and maintenance of that power plant. And the reason why is because of that reduced effect of shading, your cleaning regimen on those solar panels becomes lower. Obviously, putting guys up on roof is expensive, so by reducing the amount of times they have to clean a panel per year, it will increase will reduce your operation and maintenance cost and cleaning regimen. If we then look at the lifetime performance of your module with the solar cell optimizers, this is your traditional degradation, linear degradation of a solar panel over your 25 years. Now, if we then look at a module with the cell optimizers built in, we have an increased performance over the lifetime. And why that is because we've eliminated the mismatch of the cells inside the module, and we eliminate the mismatch between the panels themselves. We get this increased energy gain over the years. So let's have a look at some shading examples. This is an array with you can see here a pole was put in place just to simulate a shading effect. The unshaded reference gave us 19 kilowatt hours. With a panel optimizer, we had 18.1 kilowatt hours, which is a 5.6% decrease in the power. With the solar cell optimizer, with the Maxim solution, the energy production was 18.9 kilowatt hours, which is a 1.5% reduction. So effectively, in this particular instance, with your solar cell optimizer, we get a 4% increase over the best panel optimizer solution. So we can see here, if you're looking at your production graph with the shading, you can see the increased energy production out of that out of the solar panel with the solar cell optimizers built in. Mentioned it before, but in your in your soiling conditions, so this is a solar panel, and there's a buildup of dirt on the bottom end of the frame, which then creates decreased performance in that particular solar panel and subsequently the array. So this is another situation with field conditions with soiling on the solar panel, the buildup of dust. What we then did is to simulate that. We put a mesh across the solar cells to simulate the soiling conditions. Now, if we look at a comparison between normal energy production, the energy production in blue of a solar panel with solar cell optimizers, and the energy production of a solar panel with a module optimizer. We can see the difference there. And once again, looking at the energy production, with the unshaded reference, we've got 18.9 kilowatt hours. With the solar cell optimizer, 18.45 kilowatt hours, which was a 2% reduction. And with the market-leading solar panel optimizer, 15.79 kilowatt hours. So you can see in this particular instance, the performance out of a module with a solar cell optimizer is quite significant. So the Maxim solution has the best-in-class soiling performance and increased power in real-life conditions with eliminating the hotspots. So let's have a look at some real-life conditions, real-life examples where they did some comparisons. So in order to create a fair comparison, what was done in this particular array, this is an array where there are no shading. The modules were alternated. So the B represents your standard module without solar cell optimizers, and the A represents the Maxim solution. So the strings were alternated across the array to try and get an even reference throughout that particular array. And here we can see in this particular solution, where there's no shading conditions, we can achieve a 4% increase. The energy yield was 4% higher than the standard panels. Now, at another example, similar layouts on the array. And what I'd like you to pay attention to here is during the shading condition, the increased performance out of the solar panels. So what that video was showing is just the real-life performance on a real-life situation where we had shading across the array during the day. And you should have noticed on the video there that out of that particular example, the energy increase out of the array was 13% when compared to modules without the optimizers built in. The next benefit of the solar panels with the optimizers is that we get increased row-to-row performance. So this is an array where we get late afternoon shading on the strings. Once again, as soon as that shading happens, the module loses 30% of its power. With the solar cell optimizer solution, we get shading across the cell. It reduces the power of that particular string proportionally, and we get an increased energy yield out of that module. So looking at the power curves of those particular examples, looking at a module at 10 degrees, so at the 10 degrees, so the conventional model is at 10 degrees, and so that's the dotted line. The solid line is with the solar cell optimizers. So we can see here, by increasing our ground coverage ratio to 80%, it gives us this energy production region over here. So we get a much better increased energy yield out of that example at 10 degrees. When we increase that angle to 30 degrees, you can see here the energy production out of that array with the increased ground coverage ratio is quite significant. So why does that effect happen? If we look at a standard module, this is typically speaking what your power curve would look like. So you've got a maximum power point, one single maximum power point on that IV curve. Obviously, with your increase or decrease in irradiance, that single point does move depending on the power of that ray. If we then look at the the solar cell optimized solution with Maxim, what we achieve is we achieve a maximum power point tracking window. So what this means is that all your different panels can perform differently, your strings can perform differently, but because of this maximum power point tracking window over here, it negates the effect of that mismatch and the shading, and it allows the inverter to perform according to its best conditions. So you're not affecting the maximum power point tracking point of that particular inverter. So what that effect is, if you look at your row shading, if we increase the shading proportionally, so 0, 25, 50, 75, and 100%, with 25% shading, the increased yield across the strings is 42% compared to a standard or conventional module. If we increase the shading to 50%, we get a 34% increase in energy yield. Once that shading goes to 75%, there's a 24% increase, and a slight increase if we get entire shading across the module. So this was a simulation that was done on a moor in the USA, and in a conventional commercial building, you can see that this is a real-life situation. We have a big wall here which creates shading in this portion of the roof, and then the skylight which creates shading in this area of the roof. So with the Maxim solution, because of the increased yield, we can put solar cells in that shaded portion over here from the wall, as well as the skylight portion over here. And what's that helped to achieve? So in this particular installation, 2,000 panels, giving us 500 kilowatts, ground coverage ratio of 80%. The energy yield was 1.58 kilowatt hours per kilowatt installed. The annual energy production was 794 megawatt hours, and giving us a 12.4 cents levelized cost of energy. With the Maxim solution, we increased the panel count to 2,300, giving us 575 kilowatts. Ground coverage increased to 92%. The annual energy production, AC energy production, remained at 1.58 kilowatt hours per kilowatt peak. And that gave an energy yield of 913 megawatt hours. Finally, levelized cost of energy was 10.5 cents, giving a 15% reduction in the levelized cost of energy. So we get more panels, the same energy per panel, and a lower cost of energy. Let's have a quick look at the data sheet. So the Jinko module, it's with the Maxim solution. It's a 4-bus bar cell. We have an anti-PID guarantee. So the modules are tested at 60 degrees with 85% relative humidity. We've got the built-in optimizers on the cell, giving us the most flexible solution for any rooftop conditions, elimination of hotspots, and best-in-class shade performance. The benefit of this solution as well is the Maxim modules are compatible with any inverter, and the optimization is built into the individual strings. We have no requirement for any additional gateways or anything like that. If we look here at the data sheet, the specifications are very, very similar to your standard module, so there's no effect on the particular on that particular module. What that allows is, compared to other solutions with optimization, with module optimization, it gives us your design flexibility where we don't have any parameters that restrict the way we design the panels, your strings and that array. It also gives us the opportunity to have strings in multi-orientations with different levels of shading without any influence on the performance of those panels. So finally, to wrap up, the benefits is your maximum power point tracking function is pushed deep within the PV system on the strings. It gives us increased energy yield due to reduction in soiling, shadowing, and mismatch in the cells, the strings, and the different modules. We minimize power degradation over panel life, eliminate hotspots, and there's no change in the PV array design, no additional hardware, gateways, or monitoring services. And that's it from me. Thank you.
Thank you so much, Kevin. Yeah, very interesting. There's a whole bunch of stuff that I also saw. I've got one question.
Sure.
When you put up the modules,
yes.
If I understand it correctly, if there's any kind of shadowing, it's not going to switch off the entire array at all. Like it currently, let's say for argument's sake, there's a big shadow that falls over, and you don't have optic track on your inverter. If I understand correctly, the modules will still work, will still produce power.
Yes, that is correct. So when you have a shading condition, normally your module will reduce by 30% per stringlet shading. With the Maxim solution, it still performs without influencing the performance of your entire array. So if we look here at your MPPT window, so your different modules will still perform within this window when you have those shading conditions. So it does not affect your MPPT in the inverter.
Oh, that's
so your
great.
string still works.
I think that's what's setting this technology up. Yeah, we want to open up the questions now. So if anybody's got any questions, please feel free to put up your hand and I'll unmute you.
Sorry, one thing I just want to go back to as well. So you see the way in the conventional panel with the shading, what happens as soon as you've got a bit of shading, your diode starts conducting and that entire string drops out. With your solar panel optimizers, your optimizer is across the module. So even if you have a shading there, that diode still conducts, and you still lose 30% of your power in the module. With the Maxim solution, your optimizer is across each of the strings, and you don't actually have your bypass diode in there. So that MPP tracker works across the individual string and eliminates that bypass diode. So when you have a shading condition, it's the MPP tracker, it's not a hard on-off switch. So your degradation or your loss of power will reduce proportionally to that shading without affecting your module and the module performance and your string performance. So yeah, in effect, it still functions as if there was no shading effect in a standard situation where you've got the bypass diodes.
Thank you. We've got a question here. I'm going to unmute you, Linda. So yeah, you can talk. Linda, you can talk.
Okay, thank you. Kevin, good morning. Thanks very much for an enlightening presentation, a very interesting innovation. However, just need to find out, perhaps, obviously you did indicate that these cell optimizers are embedded in the module. However, just one question. In terms of maintenance, perhaps if one of these happens to get faulty, is there a way of perhaps monitoring that or even replacing it, or what is the situation in that regard?
Okay, so yes, in terms of the actual MPPT tracker, it is a small little IC. That IC actually sits across your this portion of the junction box. So we take the bypass diode out, and it sits across the string over here. So it's not actually laminated inside the module.
All right.
It's inside the junction box.
The junction box, okay.
That is correct. Sorry. So this was just a representation to show that your optimization is across the string. Okay. So that is correct. But yes, it will sit here inside the junction box.
Mm-hmm. So in other words, maintenance is possible.
Yes, it could be. However, what would most likely happen in a warranty event is that we would evaluate that module and then replace the whole module.
Okay.
So the individual, that portion of the claim would be dealt with between us and Maxim.
Mm-hmm.
And where your warranty comes in is the power warranty. So if your module is not performing according to the power warranty of the modules, then it would be a warranty replacement.
Okay. All right. Thank you.
No problem.
Thank you, Linda. Kevin, we've got another. Is it 271? Is that yes?
Sorry, can you cut out there? Can you repeat the question?
Okay, sorry. The question is the 270 watt peak the current maximum module power output?
Yeah, what I can do for you is I can send you a presentation according to our what we're currently producing in terms of the power, in terms of our power roadmap. 270 would be at the moment the maximum power for this particular solution. What we have launched this year, it's just gone into production probably about a month or two ago, is our mono PERC modules. And those particular modules at the moment we're producing 295 watts, but it is not a solution with the optimizer built in. So it's a standard mono PERC module at 295 watts.
Thank you. Kevin, another one. Can this solution be added on PV Syst and modeled with it?
Okay. At the moment, Maxim hasn't, or PV Syst hasn't allowed the actual analysis of the substring optimization. They are busy working on it. We don't have a release date yet, but PV Syst will be allowing the functionality in the software by the end of this year. We don't have a release date. They just told us fourth quarter.
Oh, thank you. I've got plenty of questions here. We'll just keep them coming. Is this technology patented by Jinko?
No, it's not a Jinko patent. The patent will be held with Maxim.
All right, thank you.
So we've manufactured the modules and they do the electronics. So it is their patent.
Okay, thank you so much. I just want to also say, if you've got any queries on pricing, please feel free to either mail myself or Russell or Matthew. One of our friendly staff members will be able to share this presentation with you after this event as well, and pricing. So please get in touch with us. Are there any more questions?
It flashed past earlier, but there was something about the energy production. How does the kilowatt hours, and then it was cut off. So I think it was from Nick.
Yeah, he asks, how can the annual kilowatt hours and kilowatt peak be the same for the example on page 20, but the LCOE is less on the optimizers?
Okay. So there's a few things that will affect the LCOE. The first one is your O&M schedule, so your cleaning schedule. That cost gets reduced. By putting more solar panels on the roof, and by having the performance increase of the modules themselves, as well as the strings and the arrays, we get increased performance just by reducing the mismatch. So that would typically, in any situation, that would give about a 4% increase in energy yield as opposed to conventional string without the optimization. Then the third thing is because of the increased kilowatt peak on the roof and minimizing the shading conditions, that will give, although your production in the shaded areas during the morning will be slightly lower, you then get your production in the afternoon or mid-morning and afternoon. So all those factors resulted in a lower LCOE.
Thank you. And one more. What are all the colors that these modules are available in? Can you get them in black?
At the moment, it is the standard blue color. They are on our polycrystalline modules. I will have to check. I'm not sure if there is a plan to put them on our mono modules, but at the moment it will just be the standard blue polycrystalline modules. The note, however, is that because it is a junction box solution, there should be no reason why we can't do it. Maybe if there are some specific requests, we can have a look at it, and I can give you a better answer on the ability to supply different colors. So the general answer is not at the moment, but it is something that we could probably look at.
Something in the future. All right. Thank you so much. Are there any more questions? Nick, are you happy? Thank you. And just want to thank everybody for your time. Thank you, Kevin. Thank you for hosting this wonderful event and learned a lot. I trust that everybody on this event learns a lot. And we're really looking forward to the next one. As I've said, if anybody needs pricing or more information, please feel free to contact us. Visit our website as well on PROINSO, www.proinso.co.za for updates on the latest product pricing and products that we've got available. We look forward to seeing you on the next event. Thank you so much. Have a great day, and we'll see you soon.
Great. Thanks, everybody.
Cheers for now.
Bye-bye.